Okay, so hello everyone, and welcome back for the second session of the day. So the second session is about AI-driven circuit design and verification automation. My name is Christos Bouganis, and I'm not going to update this now. Another time. My name is Christos Bouganis, and I'm a professor at Imperial College London, and I'm one of the leads in one of those teams. So we're going to follow a very similar structure to the previous session. We're going to have three subsections. The first one, we're going to hear from the researchers about their work that they have done in the last year. Then we're going to move on to the second part, where we have our PhD students and the Google DeepMind interns. They're going to report on their work that they have done so far. And then we're going to finish the section with listening from people who have received funding through the April AI Hub. We're going to have two talks. One is from Dr. Harris from University of Glasgow, and the other one is from Dr. Teng from University of Sheffield. So I don't want to take up more of your time. I'm going to invite first Christian to give us an update on his work. Christian.
So thank you so much. There is still people that is entering the room. As it is just after lunch, we will keep the tone at the eye level to avoid people start sleeping. So let's discuss about the research that we have done so far in this thematic area, and in particular the integration of large language models and electronic design automation. So we're assisting today to an increasing demand of the use of artificial intelligence to give help in different tasks, including electronics. There are different reasons behind this. First of all, we might have human AI co-design. So engineers, we might get important help during the design processes. And each of us, I think in the room there are a lot of chip designers, electronic engineers. Each of us knows the intricacies when we have to deal with tape out, with design space, with verification. So having a sort of artificial agent that can assist us may be beneficial to not only reduce the design time and maybe allow to us more annual leaves, but also to try to improve the productivity. Indeed, in also white papers from industries, it is promised more than 10 times improvement in productivity in the design of electronic circuits. Obviously, the fact that we use large language model allows us to abstract the way in which we ask the tool to design circuit. We use just text specification. We describe what we would like. We describe what sort of specification we would like to satisfy, and hopefully we will get the proper implementation. In addition, the fact to interface artificial intelligence to electronic design automation allows us to get faster, more optimized circuits, because also AI may assist in suggesting optimization fix in order to improve our design. However, in the research and industry spectrum, I would say, people usually propose customized tool for digital design, customized tool for analog design, customized tool for radio frequency design. So there is a limited availability of sort of unified tool that offer a flexible platform to accommodate multiple types of electronics design flow altogether. So today we are trying to answer this question. What about having a sort of unified tool that supports different circuit design flow? Do we have? The answer is yes. We are proposing a large language model assisted unified tool for electronic design automation that basically works as follows. The engineer provides the specification, the description of their circuit, as well as any design specification, any hardware objective to be satisfied. This input prompt is supplied to a large language model that is responsible for providing any sort of source file, ranging from under description languages like Verilog, VHDL, but also netlist for analog and radio frequency design. In addition, the large language model may provide some suggestion in order to satisfy more hardware requirements and improve the generation of the source file. The outputs from the large language model are thus provided to commercial EDA tool. At the moment, in the tool chain we are proposing, we support tool from AMD, Vivado, for FPGA design, tool from Cadence, Virtuoso, for analog mixed signal design, and tool for radio frequency design, like ADS Keysight. Usually, the steps that are performed are the verification, to verify whether our circuit reply correctly to our input stimuli, synthesis, to translate a very high-level description into a sort of, let's say, cell composition, and the layout, to actually place what we have in mind and route properly. From each design step, as we know in the commercial tool, we may get both report files about resource occupation, power dissipation, and delays, but also log files. And we know how verbose are these files. So in order to try to feed all this information to artificial intelligence, to large language models, to identify if something is going odd, we decide to implement also a Python-assisted report passing that take all this information and compress them in a sort of dictionary. That is basically a JSON file that can be later supplied to a large language model to say what is going wrong, what can we do to improve our design. In addition, we equipped the tool chain with sort of logging and visualization facilities in case we have a very huge data set, and we would like also to identify statistics about how things are going on. Finally, the interesting part is the linking point between the report log processing and our input prompt and specification. To do this, there is a feedback loop in which, according to the specification that we get from the large language models, we are called to edit the input specs to run a next iteration and try to get an improved design. Now, we will start investigating some case studies according to the different design flows we accommodate, and I give the stage to Pratibha that will introduce the analog design. Thank you.
So, thank you, Christian. So why analog? The world we are measuring is analog. Every signal that matters, whether it's light, sound, biomedical signals, all are in the continuous forms. So before an AI model or digital signal processing can do anything, we need analog circuits to amplify them, filter them, and interface them to the computation world. So analog is a fundamental block which connects the physical world to the computation world. So that's why we need analog. But why we need to rethink the analog design? Because still the analog design is very manual, and we build it in a very basic method. Let's imagine a designer. She started in the morning with a simpler amplifier circuits, and she draws the topology. She tweaked the W by L ratio, the width and length of the transistor. She tweaked the bias points and simulate, run the simulations. Now she's not meeting the gain. She again fixes things, again run the simulation, and now this time she's not meeting the phase margin. And again and again and again. And the time is, hours passes. And now she's in the frustrated. Now she thinks, is there any smarter way to do this? And there, she thought about asking the AI. So what AI do? So she just write a prompt, like we asked to ChatGPT, like design a 5-transistor OTA and 180 nanometer CMOS with gain greater than 40 dB and a stable phase margin. So it's just, she have given some natural language prompt and asked for some specification, and now what? LLM convert the natural language prompt to the SPICE level netlist, which can be understandable by the Cadence Virtuoso tool. So it's a spectra simulator. So you can see the netlist, and from there, she can get the 5 transistor router. So from this time, she no need to start from the scratch. Instead, the LLM provides the initial W by L ratio, the V bias points to achieve the gain. So here, we have run the 15 iterations. So you can see in initial iterations, the gain is not converging to the 40 dB, but the later it converts to the 40 dB. So why 15 iterations? It's to check how robust is our model, and it shows it's not just a lucky hit, it's the model is converging well. So here shows the first graph, which shows the gain versus the iterations and the phase margin. Because in analog, the phase margin is for the stability. So stability is equally important as the gain, because gain is to amplify the signal, and the phase margin is for stability. So you can clearly see we are getting the stable phase margin also, as she asked for, and the 40 dB gain for most of the iterations. Also, the real silicon has mismatch. The real devices have mismatch. So we just not care about the simulation, we also care about the real world. So there, I have run the simulations for like Monte Carlo simulations that has done for the gain. So it's counting for the device mismatch, and you can see it is having majority for 40 dB. So that's how we solve the problem of hours of work in few minutes. So next, I will hand over the mic to the Penyota to talk more about today, about the different domain of the circuit design.
Well, in the spectrum of radio frequency design, let's talk about antennas, where antennas, their fundamental purpose is to transmit and receive electromagnetic waves. They are very important for communication. Antennas are the link between our electronic devices and the airwaves around us. Antennas can be found in almost any device, like your phone, the Wi-Fi router at your home, the radio in your car, but even in satellite communications, they stream data from space. As we evolve in a more 5G era, antennas have a complex task. We need more complex antennas to serve the 5G purpose. So some might say that antennas are like the heroes of communication. There are different types of antennas for different applications, for different frequencies. And there are also some technical key parameters we need to take into account, like gain, how effectively antennas transmit and receive signals, or directivity, how and where they direct the signal. In the case of patch antennas or microstrip antennas, also size and the size of the patch plays an important role, and it affects the frequency as well. Another key technical consideration is the reflection coefficient, which explains how well the signal is transmitted and is reflected. Reflection coefficient is also called S11, as you can see in the plot. So the lower the S11, the better. That's a lot of information, right? That's a lot of things you need to keep in mind and to take into account when designing an antenna. But fear not, LLMs are here to rescue us. Well, you're still needed though. So in this case, we have a designer. They want to design a microstrip patch antenna on FR4 substrate at 2.4 gigahertz. Why 2.4 gigahertz? Well, this frequency belongs in the ISM band, which stands for industrial, scientific, and medical applications. It's widely used. You all have it, here and in your homes in the Wi-Fi. We have one requirement. S11 needs to be below -10 dB. So remember, only thing to remember is S11, the lower, the better. Same as before, the LLM will give us a netlist, which seems like coding. In this case, we also use a graph model to visualize that netlist and to also see if there is any link missing, if the blocks are not connected properly, if a simulation block is there, and etc. In the first iteration, S11 is not really great, as you can see, and we also have this antenna layout. Just to mention that for this case study, I used software Keysight, ADS from Keysight, and LLM model is O1. With human and AI co-interaction, we can see how S11 is slowly starting to become lower and lower according to our requirement. After 12 iterations, we reach the S11 which we wanted. And not even the one we wanted, but even better. You can see in the plot that we even reached -16 dB. And of course, you can see the difference between the two layouts, right? Well, I don't blame you if you don't. The LLM recommended an extra part, an extra feed line, to improve matching and to achieve that great S11. So trust me, this design is much better. And even if you don't trust me, just trust the LLM. Thank you. So I'll pass it on to Christian to finish.
So thank you, Panayota. And now let's move to digital design, and specifically FPGA design. Now, I appreciate that in the audience there is people of diverse backgrounds, so I believe it is important to explain what is an FPGA. FPGA stands for Field Programmable Gate Array. It is basically a chip that you can reconfigure. Basically, you have a logic function in mind, and basically every time you can rerun so-called bit stream on the chip that configure it to support some logic function. In addition, it is possible to find other modules like on-chip memories and also optimized module for computation like digital signal processor. So I would say a word in a chip. Now, in the case of FPGA design, the procedure is quite different from what Panayota and Pratibha have explained. And in particular, in our input prompt, we start from, yes, a specification of the circuit that we would like to achieve, as an example, a finite state machine, but also some specification about some hardware constraint. As an example, we would like to use a given number of logic resources, lookup table, LUT, and also a given target clock frequency. Other than this information, we provide the input and output port of our digital circuits that are defined in the bottom peak. Now what's happening? The large language model will generate the Verilog code, that is hardware description language, that represent at high level our circuit, what our circuit should do. The generation from the large language model is supplied to the electronic design automation tool, that is in our case AMD Vivado, and following the logic verification, the synthesis, and the place and route stage, we achieve the actual hardware implementation. As I was mentioning before, our tool basically summarizes all the relevant information in terms of area, power, and delays, and also the log information, whether the different steps were successful or not, in a sort of log file that is a JSON file that you can see on the right side. As you can see, other than general information about the module that we are implementing, we are also information about the execution time, both related to the large language model, how it took to generate the design, and also the electronic design automation tool. In addition, for each step that we follow, we basically flag whether this step was successful or not. Finally, we log the information that relates to the hardware metrics. So resources, how many resources we are using according to different categories, delays, and power consumption, both static and dynamic power consumption. I also said at the beginning that in the input prompt, we define sort of specification. So not only what a circuit should do, but also how, let's say, it should satisfy some hardware constraint. So basically, at the very bottom of the log file that we report, we also indicate whether the constraints that we provided were satisfied or not. Now, we exploited the tool to benchmark a state-of-the-art dataset for FPGA design that is ResBench. ResBench has been proposed this year, and basically it consists of 56 different problems that are categorized across 12 categories. In terms of, let's say, tooling, we were exploiting GPT-4o as large language models, AMD Vivado, as I said, for the actual implementation on FPGA, and an AMD Xilinx Zynq 7020 FPGA as devices. Now, in this first plot, basically, we show how was the execution time of the large language model across the different categories. Basically, the time span from 2 nanoseconds to almost 7 nanoseconds. 2 nanoseconds for very simply bitwise and logical operation, and up to 7 nanoseconds in more complex scenarios like machine learning, climate, and pipelining design. Now, we said at the very beginning, one of the objectives of this work is to boost the productivity. And actually, we were able to run all the 56 problems, 5 runs each, because we need to consider that each time the large language model will provide a different response because of its conception. So we were able to run 280 designs in less than 1 day. How much it takes if we do by us? Come on, it is not 1 day. We have many things to do. Also, as a researcher, administration, supervision, we may take months to realize all these designs. So the tool was able in just less than 1 day. Other type of information that our tool is able to log relates to the pass rate. So we said we have 56 design points. We do 5 runs for each design. Out of 5, how many times I've been successful or not? And basically, we show these heat maps here. Basically, the colors closer to the navy blue means a high rate of successful design. So the blue navy is 5 out of 5. While, let's say, lighter colors, and in the most extreme case, the white colors, means that no one of the 5 runs was successful. So basically, we have 2 scenarios. On the left side, we have the implementation. So basically, we leave the design from the logic simulation to the synthesis to the implementation, and we see if actually this is implementable on FPGA or not. On the right side, on the contrary, we take under consideration the lookup table constraints, so the area constraints. So we say, okay, the design was implemented, but actually, did the design satisfy the constraint that we defined at the beginning? So overall, we may say that the figure on the right is a subset of the figure on the left side. But I would say something very interesting that Retool is offering is what happens when we have a failure point. We are getting a design, as an example, a machine learning module, that basically is always unsuccessful. So we say, but what is the problem? We're also able, through our tool, to extract in our JSON file any information that allows us to appreciate where the problem was. And in this specific case, the problem was with the placement. Basically, we were asking too many input and output ports with respect to those available on the FPGA. So this is a message to say, or you reconceive your design to satisfy the I/O count, or you need to take a more powerful FPGA that has more I/O count. So basically, this is very important because this very summarized information can be fed back to the large language model to provide us some recommendation, especially for people that, let's say, start getting familiarity now with the design flow. And so yes, this is regarding the tool. We have explored the different parts, and now time for questions. Thank you.
Thanks, everyone. So we have a number of questions, but because of time limitations, I'm going to be able to get only one for each of the presenters. So, Panagiotis, can I start with you? So one of the question is, a patch antenna is relatively easy to fabricate and test. How close goes the simulation to reality? And what about the other parameters?
Yes, it's true. And a patch antenna is one of the reasons why it's used also in GPS and Wi-Fi, because it of ease of fabrication and test. That simulation is not the electromagnetic simulation, so I suppose there would be differences between the electromagnetic and the simulation offered by ADS. Other parameters, I suppose that is apart from the S11 that I talked about. There is parameters, for example, the length and the width of the feed line and the patch. That needs to be considered when it's for fabrication, because some widths may not be like properly fabricated if it's too small, for example. So when and if we reach that stage, this should be taken into account.
Okay.
Thank you.
Okay, thanks. So moving on, one is for Pratibha. How do you prevent the LLM from giving unrealistic design suggestions?
Yes. So LLM is put into the simulation loop. So if it gives the unrealistic values, it will get rejected by the simulator itself. And also LLM is not handling the important physical parameters related to the device. It's just handling the width and length and some bias point related to the device. So it will be automatically rejected by the simulator. Yes.
Okay. Yeah. Thanks. And Christian, are you considering exploring additional AI models for FPGA design on optimization?
Oh, thank you so much for the question. This is a very relevant question. So yes, we're actually working toward this. And basically, one model may be the exploitation of graph-based neural networks, because we may represent circuits as graphs, and this may facilitate a better understanding on the relationship between the gates, and in addition, to help as a repairing tool in case something is odd with the Verilog design. In this prospect, I would say also reinforcement learning may be an interesting strategy. And there is a lot of research ongoing toward this. So I would say yes, reinforcement learning and graph-based neural networks.
Okay, great. Okay, thank you very much. So yeah, thanks everyone. Yeah. So we had more questions in Slido. So all these will be answered and podcasting later on. So if you go back to Slido, you're gonna be able to find the answers to those questions and other questions. So I would like now to move to part 2, which is about the PhD students that have been doing work related to the April Hub and also been supported by the Google DeepMind. So, we'd like to welcome Sami. Yeah. So this will be very short pitches. Please come in. Very, very quick pitches, just for people to tell us what they have done very, very briefly. Yeah? Okay, thanks.
Thank you very much, Christos. Good afternoon, everyone. The rise of AI is phenomenal. And today, we've met with numerous magical tools that provided by the enhanced machine learning capabilities. Many traditional algorithms that have been heavily relying on mathematical algorithms have now been replaced with more smart and perceptual AI models. However, all these prosperities come at an intense computation power that results in intense massive power consumption. My name is Semih Vazgeçen. I'm a first-year PhD at the AI Hub, and my research focuses on enabling sustainable AI implementations on resource-constrained devices, namely edge devices, such as drones, and also effectively addressing the low swap capabilities like low size, weight, and power. So in this spectrum, I developed a face recognition application that specifically targets non-frontal aerially taken images. So let's think about a drone-driven surveillance scenario. You have a drone operating at a certain altitude, and you have some subjects on the ground. And because of the distance and angle between the drone camera and then the individuals, the captured images are not perfectly frontal, but they only contain a part of these individual faces, which makes the whole recognition process challenging. Oops, sorry. Okay, which makes the whole recognition process challenging. So thanks to our model that orchestrates two novel approaches, first, we're utilizing a generative adversarial network to be able to frontalize the non-frontal images into their frontal versions by reconstruction. And then once we obtain these frontal views of these individuals, we are using our energy-efficient, Memristor-based sustainable classifiers. So at the end of the whole pipeline, we're able to identify who we're looking for. So why this whole process is energy efficient? It's obvious that the Memristors are two-terminal analog devices, and it's obvious that they consume way less power than digital devices. But also, this interesting fact is, these are work in an event-driven mechanism. Well, what that means? So in traditional computer architectures, let's say CPUs, they have a global clock that ticks at a constant speed that may change over time. But these Memristors are working event-driven scenarios. So think about your finger, and then you hold it. It doesn't hurt, right? But you feel it. But you firmly squeeze it, it hurts. So this is basically how Memristors work. Thank you very much.
So our next speaker is Eleni. Let me just go down.
Hello, everyone. I'm going to ask you a very simple question. Have you ever tried to generate an image or just to fix it using an AI model? I'm pretty sure that if you have, you know that this requires some seconds or some minutes. Now imagine trying to do that real time, running directly on your phone, a camera, or a drone. My name is Eleni, and I'm an electrical engineer doing my PhD in April's AI Hub. My PhD focuses on hardware accelerator of image application on edge devices. In today's world, these models run on cloud. They have incredible realism, but this comes with a cost. They have high latency, as data has to travel from cloud to our devices, and also they are very computationally expensive. Through my PhD, I'm trying to find new hardware architectures in order to reduce the computational cost of these models in order to be running on edge devices. With this, not only our generative AI models will be faster, but also more energy efficient and privacy preserving, as data doesn't have to move from our device. So in one line, what I'm trying to do is to move generative AI models from cloud to the edge. Thank you.
Our next speaker is Matt.
There we are. Hello. So I wanted to start with a question. How many people here have been frustrated by the output of generative models? Anyone? Yeah. I know I've been. They can output hallucinations or not follow the requests that you put in, and the problem only scales from here. So my research looks to help us all in this problem, asking how can you improve the output from large language models using iterative feedback, and specifically targeting hardware design. And I'll give you a clue. I think the answer lies in the slide behind me. So my name's Matthew Youngman. I'm an AI researcher at the April AI Hub, and I have a background in digital design spanning academia and industry. And I'm here to talk to you about iterative feedback loops. So presently, in typical design flows that electronic engineers use, they program hardware description language code, which is hardware that describes the circuits and systems they're trying to build. This is a highly manual and iterative task that jumps back and forth between adapting the code they're writing to pass specification and design checks. Our team, as described earlier, is using generative models to help in this process, allowing clueless users to get the required designs. However, as I mentioned already, generative models often output errors, and as a result, these often fail the design flows. Therefore, I'm looking to implement a corrective guidance system to fix errors, improve power performance and area metrics, and tweak the parameters controlling the design flow. This means that any erroneous code generated by the models doesn't have to be wasted, improving the efficiency of the system and improving the quality of the design. Yeah, thank you very much.
Our next speaker is Sue.
Hi, I'm Sheaf, and my research is also about making the hardware design as intelligent and adaptive as software design, just like what Matthew, but my side is more on the verification side. So this summer, through the Google DeepMind's internship at the April AI's Hub, I built a prototype where AI acts as a co-engineers that using large language model to read specification, test the circuits, and highlight precision issues for the engineers to make better decisions. So all through a fully automated pipeline to reduce the time and labor costs at the same time providing a full automation. Oh, and now I started my PhD now, aiming to scale this into a AI-driven hardware design loop where AI and engineers just work together, co-engineers continuously, improving the circuit design into a real innovation across AI chips, robotics, healthcare, electronics, and sustainable systems. And I believe that the next generation of chips just not only run AI, but also AI would co-design itself. Yeah, thank you.
Another speaker is Eva.
Hopefully it's not too high. So how many of us have ever been stuck running a bunch of simulations? Oh, sorry. There we go. How many of us have ever been stuck running a bunch of really boring simulations for many multiple settings? I can certainly say I have. I've spent loads of my summer time running many simulations, and it's one of the most frustrating things when you know that you could be doing something else if an AI took over that. So my name is Eva, and I'm a PhD student at the April AI Hub, and I was also one of the Google DeepMind research interns this summer. And this is what my project is trying to solve. So what I'm trying to do is to get a circuit representation in the form of a sheaf, which comes from the algebraic concept of algebraic topology, and get a sheaf neural network to learn this automation process so that we can end up with an optimized circuit that saves power, area, and components in general. So by learning this process, we can be saving time for the engineers who don't have to run the really extensive simulations that are required at the moment to get from a fully non-approximate computing, non-approximate circuit into a fully optimized approximate circuit that does the same task but saving quite a lot of power. Thank you.
So great, thanks everyone. So moving on to the questions. So we have a couple of questions. Take the first one, Semi. How can the model create a full frontal face if it has only seen the person from an angle?
So this is an interesting question, but the main point is here, if you're looking for somebody to recognize it, you have to know this person beforehand. For as an example, when you are applying for a passport or driving license, whatever it is, you're providing your biometrics to the government or authorities. So the government or whoever looks for you has basically got your information beforehand and is trying to find you in somewhere. So we train our model with these ground truth information taken beforehand, and then in this case, we're able to enable the model to recognize you at a given time. Yeah. Okay, thank you.
Okay, thanks. Moving on to the next one. This is for Eleni. Why is it important to make AI models run efficiently on edge devices instead of in the cloud?
As I said, we have many benefits if we run, especially generative AI models on cloud, because we have, first of all, they are faster, they are energy efficient, and also we can have privacy because data doesn't have to move. And also these can open us to many new applications, like generating or fixing the resolution of images real time on cameras or drones. So yes, I think it is really important, and there are many benefits of that. Thank you.
Okay, thanks. One for Matt. What are the major limitations of large language models in hardware design?
Yes. So I think there's kind of three limitations at the moment. The first one is the context window. So you can only put in so many tokens into the large language model, which kind of restricts the context that they can get for the design that you're making in any form. And this really means that you can't build out hierarchically very easily. So you have to kind of break down your design into smaller modules, which can cause problems later in terms of then synthesizing all these modules together. And the second one is kind of the data limit. So specifically, if you're looking at hardware design languages, there's not a lot of information out there that's publicly available or open source to train your models on. And then finally, the third one is explainability, because large language models are black boxes. You can't really explain what the decisions they're making are. And this is very important to engineers because it can take a long time for people to design these systems.
Okay, thanks. I will take the next one for Sue. How does your AI system ensure accuracy and avoid generating incorrect Verilog or tests?
Yeah, I have to admit that for a large language model, it's quite impossible to make sure that it 100% generates correct or what the task that we want. But here I use this to enforce some specific constraints to it, to reject some of the incorrect scripts. At the same time, to introduce another supervision, like another large language model agent to revise if it's going correct. Also, at the same time, human engineers can always review and audit the logs.
Okay, thanks. And I will take one more, the last one for Eva, actually. What hardware information does a Sheaf neural network need?
Well, good question. I'd say mostly anything that can inform the pruning or the optimization process. So for a gate, for instance, where you might be able to, you might want to attach information such as the toggle count, the activity, the time, the type of the gate, because that information is going to enable the Sheaf neural network or the Partitioning AI, whatever, to make an informed decision. So any information that can essentially inform the pruning process can be added to the Sheaf neural network, which I think is the main strength of the model.
Okay, great. Okay, thanks. So there's actually one question for everybody. Can we have it on the screen, please? There's one question for everyone, for all.
I know the question was, what other models can you use beyond a large language model?
Yes, are there any other AI tools that you think should be used for this circuit design beyond LLMs?
I have an idea. I think reinforcement learning is very key as well, particularly in the field that I've been looking at for the corrective guidance. You can kind of take in power performance and area metrics, so the PPA metrics, that are output from the synthesis runs and kind of feed them back in, both to train your large language model and also improve the system's behavior to then get better PPA metrics. So over time, you can begin to optimize these circuits using reinforcement learning.
Okay, thanks. Anybody else would like to contribute?
Yeah, I will also add a little bit about like semantic or symbolic related specific methods. Sorry, but I can name like some like exact methods. But it do help, especially for when we are designing chips or logical scripts, that things are connected together and very complex. Yeah.
Okay, thanks.
Well, I guess not to plug in my project, but I'm working with graph and Sheaf neural networks, and I think that's certainly something that could be quite useful in terms of for circuit design, circuit optimization. It's a great way to represent circuits. It stays really true to the nature of how circuits and netlists work. So I think that's certainly a good way to move forwards.
Okay, great. Okay, thanks everyone. And you're going to have the opportunity to talk to the researchers during the poster session later on, during the coffee break. So I would like now to move on to the next section. Just a reminder, please, use the QR code to access Slido. And before we move on to the actual presentations, I would like to briefly mention about the seed funding that AI Hub provides to support projects in the related area. What you can see here in this map is the number of projects that have been supported or have been agreed to be supported by the AI Hub in the domains of circuit and system design and test and verification. So as you can see, this span across the whole UK. You have university projects from University of Glasgow, Queen's University of Belfast, Edinburgh, Herovat, Southampton and Sheffield, and of course, Newcastle. So what we have now with us, we have people that represent two of those projects. One is from the University of Glasgow, and our speaker is Dr. Harris, and the other one is Dr. Teng from the University of Sheffield. So we're going to start first from Dr. Harris, talking to us about what they are doing in their project.
Thank you, Christos. So my project, my April seeded project is SECDA-DSE, Automated Design Space Exploration of FPGA-based accelerators. So I'll just quickly go with the motivation behind this work. Thanks for Christian for explaining FPGAs, and others have also already covered accelerators for AI, but one of the main concerns we have in this space is designing these specialized FPGA-based accelerators for AI is very time-consuming and requires extensive hardware expertise. These hardware expertise come from people doing their PhDs or designing in industry, and needs to be translated through a lot of time and effort to create new designs. One of the ways we reduce that time is by creating hardware architectural templates, which can then widely be adjusted to simplify the design process further down the line for the target problem. But the problem still remains. Creating these hardware templates is a manual process, and again, still requires a lot of expertise, even though they will require less time. So the solution is try to use LLMs to efficiently explore the design space and to generate as many hardware designs quickly and the hardware templates quickly using design methodologies like one I've developed called the SECDA design methodology, which takes into account the software and the hardware design components for new AI accelerators. So with that, I kind of briefly present what the hardware software design methodology is on the left, and then what we do in this project, the SECDA-DSE. So to quickly cover the SECDA methodology, it requires two design loops. One is based on System C simulation. So System C is a hardware description language and also a simulation language. And through this, we can quickly iterate over many designs without ever having to do hardware synthesis or logic synthesis. And this will allow you to get to a better quality of design much faster without ever having to use the FPGA and hardware synthesis. Ideally, we can also use the same hardware description in System C that we created through the simulation to do hardware synthesis without changing any of the code. So basically, you press one button and you just wait a while, and you will have a hardware that you can map on, a hardware bit stream that you can map on your FPGA. So with that, you can verify your performance and then maybe identify bottlenecks that wasn't caught during the simulation. So with that design philosophy explained, SECDA-DSE looks to improve upon that, because the first design philosophy requires expert user to understand many different components and make changes to the design. SECDA-DSE basically takes the target workload, so whatever AI models that you have, takes the target device, so your AMD FPGAs, your Intel FPGAs, some architectural directives, so what kind of data flow your architecture wants, is there micro ISAs, is there is there a systolic array, or the architecture of the accelerator that you want. Takes these information and using the pre-existing SECDA-based tools, which there's a bunch of libraries that help the hardware experts work on, and things like MCP protocols that are developed for our SECDA toolkits, we can essentially alleviate the pressure on the hardware designer by automating this process. And this will generate architectural template that's compliant with SECDA tools. And then with that template, we can do some hardware parameter search. Again, the SECDA-DSE, the LLM that we fine-tune within the SECDA-DSE process will be able to choose the hardware parameters. And then finally, that will produce the finalized hardware accelerator designs. With the designs, we go back to the SECDA design methodology where we do the simulation loop and the FPGA hardware synthesis loop. We get performance results. We feed this back into a cost model database that's used to update the SECDA-DSE tool. And again, this is an iterative loop where we improve our code generation and refinement stages by taking the results of both the simulation runs and high-level synthesis and logic synthesis runs. So in terms of progress of this project, we're at the point of accelerator data collection. So I think one of the previous talks mentioned, one of the problems is to get a large database of hardware designs. So this is something that we're working on. And additionally, we're working on core integration and MCP protocols. Just to quickly explain what MCP protocols are, it's a way of LLMs to understand the functional capabilities of your framework. So let's say you have a tool that adds two numbers, and MCP protocol says, hey, look, there's a function there that exists for the LLM to understand that and to use that for function specifically. So yeah, that's mine. Thank you.
Well, thanks, Crystal. So hello, I'm Tian Tai from the University of Sheffield. So the project is about the AI Copilot automated system partition. So I actually do this project with Dr. Mohammed Isa, which is there, and Professor John Goodenough. As John is not here today, so I'm wearing this shirt, on his behalf specifically. So basically, when we do a chip design and FPGA-based accelerator design, we have loads of EDA tools and loads of steps. So we probably first do the system-level partitioning, modeling, blah, blah, blah. And then we probably have HLS or not, or directly go to the RTL. Then we go through the design compiler, synthesis. Then we probably have the PNR, place and route. And until the post-silicon measurement, actually, every step we have dedicated EDA tools for that. And for this virtualizer, it's basically some tool that give you the capability of implementing some software on it before you get HDL ready. And along this tool chain, you probably get a relative accurate power performance and area at that step. Well, relatively accurate. And you get some of the non-functional parts like the clock and power distribution, weight size, how to debug the system, how do you use the system at this stage. And then you get all of your non-functional parts by the end of the post-silicon measurement. And when are these non-functional parts stuff decided? It's probably when you are trying to partition the system, when you're trying to design the plumbing of the chip. And see, that's a long path of that. So our question is, or this project is, can we actually add another design layer before that using the generative AI to help us to predict, okay, here is my design system partition, how is it going to be like by the end of the post-silicon stage? So, well, forgive me for the ugly diagram. We have a prettier one, but didn't update on time. So on the left-hand side is our design and logics, basically the functional parts. We have our applications, data flow algorithms, blah, blah, blah. And it is basically divided into different layers. At the top, it's the application, then it's the architecture, IP level, verification, validation. And on the right-hand side is the physical, non-functional parts and the physical constraints, size, weight, cost, power consumption. So basically, you have more budget on your power consumption, you probably can afford more, well, a faster chip or more performance. If you put more area, your performance is up and your power always up. So basically it's a quite big trade-off between, not only between the PPA, but also between your cost, your budget, and what's the final product you are going to get. And then about the system utilization is the plumbing, security, how do you debug the system? Not only when you make it, how do you debug it? Also, when it's tape out, how the users is going to use that. So, to balance those, basically, we are trying to do a study of the possibility of using generative AI to balance all of these aspects and see if we can do a system-level generation, not only on the top-level module in the RTL, but also on the non-functional and functional parts, all of them together. And then see if we can capture any features of the design on the very early stage and set up the roadmap of the future generative AI in system partition. Thank you.
Thank you. So we have now time for questions. So get the first one. Beyond fine-tuning existing LLMs, do you envision developing your own custom model?
Can you hear me? Yeah. So I think this is a very challenging task because LLMs require a lot of data, and it's not clear to me that it's also required. Our focus is on enabling expert designers to design hardware accelerators faster, not necessarily to replace the expert designers, because we genuinely believe, I think there is still need for that. LLMs cannot completely replace some intuition and also requirements that cannot be expressed in LLMs currently. Maybe if we have enough data set, we could learn that, but unfortunately, I don't think it's possible without having a larger data set to work with. So fine-tuning currently is probably the best way. Yeah.
Okay, thanks. One now for Tiantai. Do you plan to explore how Gen AI could generate test scenarios that drive the designs into worst-case power or time corners?
Yeah, firstly, estimate or explore the worst-case scenario in hardware design is always the key, because we never, we can't, basically, we can always expect something worse happen in the hardware design. So, yes. I am going to explore if the generative AI could actually give us a quite accurate worst-case scenario estimation. But how do we do that? We probably rely on my lovely PhD student and the research associate over there is filming me. But also, I think from our current approach is we feed the generative AI, AI agent with quite a lot of existing designs and put the corresponding system specs along with it as kind of a database for our AI agent. And also we have another overlook AI agent full of rules to see if the generative stuff is actually make any sense. I'm not sure if that's answer your questions, but thank you.
Okay, yeah, thanks. Tiantai, one more for you. Can you say more on the non-functional parts you are interested?
Yeah, well, actually, there are quite a lot of non-functional parts, like thermal of the chip, apart from the size, weight stuff. But currently, one step at a time, and basically, we are trying to get the power distribution, clock distribution, and the debug of the system as the major task for the project.
Okay, thanks. Jude, do you plan to explore digital ASIC design after the FPGA flow?
I think this would be interesting to do. I don't think it's a priority for us because we want to focus on FPGA-based designs. As the AI space is evolving very quickly, the designs of accelerators will also need to evolve quickly, and it might be that we will use multiple models that we can swap in and out FPGA bit streams that are more efficient for those. So yes, I think we can have an area of our focus on digital ASIC design, but our main focus is on the FPGA flow.
Okay, thanks. So for both of you, actually, what is your overall experience with April and synth funding so far? And please be honest.
See, he's trying to think about something honest. Right, so firstly, thank you, Christian. Basically, we have quite a long process from the proposal stage to the last year's April submit, and to modifying the proposal. And then it's the final stage of like the announcement, contract setup, and basically Christian is there on every step supporting us. Well, many thanks, and also thanks for all the stuff in the University of Edinburgh. I know there are some negotiations between probably Sheffield, John, me, and Edinburgh, but we actually solved all the problems. So very lovely stuff, very supportive stuff. Also, I'd like to thank all the staff from the University of Edinburgh giving me this opportunity to be here. I'm actually on the leave from Sheffield, and I came back from China yesterday. It's really nice to actually do another presentation about my project on this very special, very nice scenario. Thank you.
Okay, thanks.
Honest.
Honest. Yes, Jude, yeah.
As the technical leads for the project, it's been smooth sailing for me. So thank you for Christian again for that. Yeah, it gives us an opportunity to explore something that we wanted to with our underlying platform, which is the SECDA platform. And yeah, I think it just works perfectly well with what April's initiatives are. So thank you. Yep.
Okay, perfect. That's good. So, do we have any other questions? Please, Errol.
As you look at LLMs for this general design automation area at the beginning, we talked about analog circuits. I was just wondering, how do you consider two aspects? One is the benefits of LLMs, relatively high, order of 10%. In a lot of statements that they have produced when the text is a little bit long and precise.
So two aspects. One is the relatively high error rate. So do you have to sit an expert behind every LLM to check whether what it has produced is correct and go over it? Because that is what you have to do when you're dealing with texts about human beings or situations and so on. The second question is, especially in relation to the examples you took in analog circuits, when you start using LLMs in that context, you are in a certain sense defeating the original purpose of using analog, which is saving energy. You're ending by the amount of installed energy consumption even before you start the work. With the machines that you have to have there and with the software that has been developed and the learning that has taken place, doesn't all of that defeat the purpose of having very low energy systems at the end of the day?
I can take the first part. So,
yeah, me too. But sorry, because I don't know the answer of the second part.
I can try it both, but so the first part, I think the things that have changed across essentially the last year in regards to LLMs is we're using them in a smarter way, right? We're not just using them to produce text. We're connecting them with existing frameworks that are verified. So what do I mean by this? There are software frameworks that provide human written code that LLMs can call through model context protocols. This basically gives LLMs tools to work with. Essentially, before LLMs were just, they only had hands to work and create whatever. Now they have, JCB, whatever, to create whatever you want to do. And so essentially it shortens, or rather, it adds a verification process, because now that you have a tool and you're using a cookie cutter, if you're using an LLM through that cookie cutter, it will produce something that is valid most of the time. So it kind of alleviates that problem. And then the second question, it's a realistic concern that you are trading off. It's like, right now you're losing power by using LLMs, but in the long term you might gain efficiency by running in millions and millions of these tiny devices. It's an answer that you can't realistically give a proper answer to, or it's a question that you can't really give a realistic answer to, right? It's just how the time goes on, right? It's the same kind of question with solar panels. Is production of solar panels worthwhile in the long run? Most people think they are, but you don't know, right?
Thanks.
Yeah, I want to just add one sentence. See, on the traditional EDA approach, or the conventional one, for the RTL, we have the VCS to do the verification. Every step we have verification. So why not? There's no verification approach for the generative stuff, or something AI generated. We should have a way of actually verify that it can go to the next stage. Yeah. But we still don't know how to do that which is the best way yet. So that's why I'm exploring this. And for the second part, every minute, millions of people asking questions to the ChatGPT that will consume tons of energy, and why not make it, something more productive?
Okay, thanks. Anybody else? Yes, please.
Yeah, very general question about copyright and patents. So obviously, when you start using LLMs and it's getting data from the cloud, how do you ensure you're not violating copyright or patents? And also, if the AI produces something, where do you stand with copyright and patents?
Okay.
You go first.
Okay, so this bit of the gray area at the moment, because we don't be quite responsible for using AI and whatever data is behind it. But the human has to actually filtering all the information AI gives us. I think that's quite some intellectual work on it. And currently AI cannot be an author of any paper, well, not yet. So I think that's eventually going to be a problem when AI gets smarter and smarter, but not like my pay grade to concern about at the moment.
Yeah, thank you.
Sorry.
Yeah, Jude, you want to add anything?
Yeah, I don't think it's a solvable problem. I think we are at the point where it will seep through research, and it will be part of the way we work. We will use AI, and we will use copyrighted and other people's IPs. It will just be part of the system. I don't think it's a solvable problem. That might be a pessimistic take, but it's not necessarily a bad thing. It's just progress as human race. We use tools that was previously created. That's all.
Okay, thanks. Thank you. I think we have time for one more, if there's one more question. Any more? Yes, please. Yeah. Thanks, Christian.
Thanks. So I'm just wondering about the international scope of things. And regarding all your models and data and so on, there's increasing restraints, if you like, that governments at least want to put in place about not sending your data overseas and models and accessibility. How do you see that playing out in your kind of world in terms of how it may impact even things like international collaboration, say?
Quick answer would be whenever we're doing fine tuning, we have more like we're working with smaller data sets, which we have control over. If we're fine tuning models that previously exist, that are trained by large corporate, the onus is not on us anymore. But at least the fine tuning component, it's on us. But it's a smaller data set, so we get to control that. That's as much as we can kind of do. It's just a matter of if we work with larger models or develop models from scratch, then those companies really need to take care and make sure they follow the laws. But as researchers, it's a very hard thing to do because we're limited with funding and resources.
So basically, on the research side, we are trying to use public available stuff for testing the generative AI or do a small part of the retrain. And basically, we are relying on the OpenAI OpenAI product. And the problem is the OpenAI actually doesn't store the history or share our history record to anyone else. So I think the data security is quite nice with OpenAI. And until some government sue OpenAI, I think that's probably fine at the moment.
Thank you. So, thank you very much for your input. So, you'd like to say something? Yes, please, yeah.
Good afternoon, everyone. I joined April AI recently, early this month. We have got a range of expertise, people from design, optimization, which gave me a holistic view of EDA and AI for electronics. My expertise is verification, more specifically on formal verification. I heard Professor Tantai speaking about verification. So one of the problems that I'm addressing is how do we trust the output of AI, right? And there's been a lot of work going in that direction, and I'm focusing on using formal verification, approaching it using mathematical modeling to give correctness guarantees. I'm looking forward and excited to be part of AI and to contribute to this verification part. Thank you.